Hello and welcome. On this video, I talked about this poke, which I learned about from this blog, link in the description, which has the magical effect of sticking. I call it the sticky poke because after you use it, you can then poke the VDG to whatever display mode you want, and it will stick there. It won't snap back every time you go back to the text screen or you start typing or anything. So in that video I said I need to make a video to talk about how this works. And in an upcoming video I will talk about how that works. This is that video where I talk about how it works. Let's find out. So first let's start with a review. A while ago I posted this video where I changed the start address for the video screen buffer so I could peer into the inside of the basic working storage. An issue with this is that it kept on snapping back to the regular screen buffer start at hex 400. So I found the place inside the ROM that was snapping it back, and I went and I changed it directly so it would always ensure that the start address is what I wanted rather than what it wanted. And then more recently, when I was checking to see whether my Coco 2 has the T1 chip for the video display generator, I used a much simpler poke that would prevent the snapback, and it would let me directly do whatever I wanted to the VDG by poking into the VDG addresses and ensure it would never snap back. So this video is about that poke that ensures that we won't snap back. How did that poke work? And was that poke related to the stuff that I did a while back when I ensured that the start address wouldn't change? So we'll start with that great piece of literature, Color Basic Unravelled, and we'll take a look at what's happening at hex address 167. We see this is an RVEC, 3 bytes for an RVEC for console out. And if we scroll up a little bit, Unravelled is explaining that these are different RAM vectors. So what is a RAM vector? So let's start with a problem. Let's say that you were one of the original designers of the basic ROMs, and you knew that at some point in the future you were going to add an extended color basic ROM and a disk extended color basic ROM. And maybe you weren't done coding those up yet. Maybe you had an idea of what they would be, but you don't know what they are exactly. And you do know that your customers will not have those ROMs. Your customers will happily have this ROM, but for a long time they will not have this. And what if you wanted to make a call from here to here? For example, let's say with PutSure, there's very few things where you could put a character to. You could put it to like the screen or a cassette, but you knew that when Extended Color Basic came along, you might want to be able to put a character through the serial port with the deload or desave. And maybe with Disk Extended Color Basic, you'd want to put a character to a disk, but you don't have that here. But you want to be able to call into here so that it would work when these are here. But they're not here yet. If you just made a call like this, what would happen before your customer ever got that ROM? A, they don't have the ROM for it to call into, and B, you might not even know exactly what address to call to yet, because maybe you're not totally done with those ROMs. So if you hard-coded in a call from Color Basic into that ROM, it would go nowhere good. So how do you fix this? How do you deal with the fact that in the future you're going to want PutSure to behave a little bit differently, but you can't really hard-code any kind of call into the basic yet? Well, the answer is, as often it is, indirection. So instead of directly calling, create a RAM vector. So this is just a few bytes in RAM, and the keyword here is RAM. So it can change as the computer boots up. Now when the color basic needs to make a call, let's see as part of the put your routine, it would call into here, and then this would jump into wherever it needs to go, either the extended ROM or the disk extended ROM, or maybe both. And it would be up to this ROM to initialize this RAM vector. So whichever ROM needs a hook, they tell the RAM vector, I want you to call me. And you can even have a chain of these things. So maybe extended color basic will have its own modification, disk extended color basic will have its own modification. And then we could have a chain of these, but just for simplicity's sake, imagine we just have this one section and it has this one place that it can go. What would that look like before your customer got these new ROMs? Well, you could just have your RAM vector immediately return. So rather than jumping anywhere, this arrow is just a JSR, jump to subroutine, and then this arrow is just the result of an RTS. In the future, that JSR stays put. There's no change in the future to where that's going to go. The change happens here, and instead of RTSing, it'll just jump somewhere else so it can do some extra work that this was not capable of doing. Now you might be asking, what does this have to do with making the VDG like stick with where it's at rather than changing back and forth? And well, the answer to that you actually saw in a past video. In this video where I had the ROM, I hacked the ROM to hack the VDG, I was changing bytes that would change the start address of where the video memory was, and I changed that in the ROM. And that happened in a routine that this RAM vector jumped to. So there was some place in here that was doing all of this snapping back that I didn't want it to do. So the way that I handled it in that video is I changed the code that would snap the video buffer to be 400 and made it instead just not change it. I made it be what I wanted it to be. But that sticky poke uses a totally different tack. It says, rather than trying to figure out where this is going and changing stuff in here, why not just change this RAM vector and make it go back to what it was before, just turn it into an RTS. And that's exactly what that poke does. It pokes the code for an RTS instruction in that first slot, so it's like you're back in the old color basic days. So let's use XRoar, and we're going to try a bunch of different combinations of different versions of the color basic ROM, the extended color basic ROM, and the disk extended color basic ROM. And let's peek into this RAM vector. Let's see what's actually there normally before our sticky poke gets involved. So let's start in the beginning. Color basic 1.0. When was the last time you saw this startup screen? It seems so tiny, doesn't it? And there's no reference of Microsoft? This is very strange to me. Okay, let's see what's in those memory locations. Not sure what I did wrong here. Does color basic not know hex? Oh my gosh. Does it not know the question mark? It doesn't know hex. Oh, for crying out loud. Okay. What about this? Is that bad subscript? Yeah, so it thinks this is an array. Man, you just gotta make it hard for me, huh? Jeez Louise. Alright, I guess we're not doing hex today. Let's start over again. This is really gross. Okay, thank you so much. So 57 is hex 39, so we'll just have to make a mental note of that, and we'll come back to that later. We're at 1.1, still that same tiny little copyright message. I don't know what's wrong with me. Alright, those same 57s. Gotcha. Same 57s. So these have never changed in any of the color basic updates. So let's now try the latest color basic with an extended basic. So this is color basic 1.4 with extended color basic 1.0. And so the extended color basic wins the battle of who gets their version shown on the startup screen. And finally, Microsoft enters the picture on the startup screen. And I assume I can start using hex now, like a civilized individual. So hex it is. That's 167. And these are radically different. Let's make a mental note of these for later. And these are exactly the same numbers as we got before. Let's move on to disk extended color basic, my friends. And it has changed again. 7ECB4A. Well, that's interesting. All of the extended color basics were the same, but the two disk basics are different. It's worth noting that the color basic Unravelled book also tells us these addresses, and the addresses that I found do perfectly match. So 8273 is what we saw with extended basic, and then these two addresses is what we saw with disk extended basic. The 7E is the jump instruction. This is the address that actually calls the RAM vector, which I was not actually peeking. So let's see how this RAM vector gets initialized. Let's watch that in action using the MAME debugger. So when you start the debugger, it breaks in before anything happens. So at hex address 167, we're all just sitting at FFs. So I'm going to ask it to set a watch point at 167, 3 bytes long on a write. And let her rip. Okay, so first thing we see is it looks like we got a 0 hit here, and where are we? We're at A079, and A079 is right here. So actually the change happened at the instruction just before it, which is here. So we're in cold start entry, and we're loading our X with just before the video RAM, and we're clearing the first 1K of RAM. So we're going to expect to see a couple more zeros as this clears them out. So let's watch that happen. Boom, stopped again. Now that guy got cleared out. Boom, stopped again. Now that guy cleared out. Let's see what happens next. So we're running, and now we're sitting here at A0C2. Well, A0C2 is here, but of course it's the instruction just before that's doing what it's doing. And here's where we fill the RAM vectors with RTS. So the return instruction is getting set here as we start up. So we've got our 39 here, and if we advance, another 39, and if we advance, another 39. Okay, let's keep going. Now we're stopped at 8071. That means we're now in the extended basic Unravelled book. We're in the extended basic ROM, and we're right here. And what are we doing? We're modifying the RAM hooks for the new routines contained in extended basic. And we're right in the console in, console out. Actually, this is the console out area, so these three are getting set. These two, the vector, the RVEC3 is getting added there. We just added the 7E here, and what will be next? The 8273. And as you may recall, the 8273 is what we saw when we just had extended basic and we did the peak. So that's how that gets set there. Let's see what happens next. Now we're at C040. I wonder which ROM that comes from. If you guessed disk basic, you are correct. So here we are moving the RAM vectors from ROM to RAM, and this is the line where we do our jump. And then at C044 is where we stored the address that we're going to jump to. And we wrote a CC1C, which is just what we peeked when we did Disk Extended Color Basic 1.1. So do you think we're done? You think the watch point's going to get hit anymore? Anyone else going to change this? Nope, looks like we're done. Unless, of course, we were to poke our own thing in there. So it's worth noting at this point, is there a problem with taking a RAM vector that's supposed to point here and then deliberately pointing it back to here? If you were to do that, would you run into problems? Of course you might, because any of this new stuff you might be depending on has suddenly disappeared. So for example, with putcher or console out, no longer can we write to the serial port. No longer can we write to the disk. Sure, we're not snapping back to hex 400 and the default alphanumeric internal display mode of your VDG, but we're missing other stuff that we probably need. So the hack that I did way back, where I changed the ROM routine that we went into to just surgically change what we needed to change, is probably safest. But if all you want to do is experiment and do a little poke and see if you have the T1, or see what happens when you change the start address to somewhere different in the RAM, there's really no harm. Just be aware that you're skipping stuff that, if you were doing real work, could be a problem. So to summarize, that sticky poke changes the RAM vector. The RAM vector normally either returns back where it came if you're in an old ROM, or it would jump to some new code if you had a new ROM installed. And instead, we just turned it back to the old style that would just return. So we saw the peaks that proved what the RAM vector had. We saw the writes to memory that showed how the RAM vector changes. So a couple thank yous. First to this blog for first introducing me to the sticky poke. Of course, as always, to the Unravelled series. And finally, if you want to learn more about RAM vectors, I highly recommend these blog posts on Subetha Software. These are really nice, thorough explanations of RAM vectors, and they were a great read.